For years, we've heard that quantum communication is the one thing that's truly 100% unhackable. It's supposed to be this perfect, unbreakable digital seal. But what if I told you that seal isn't quite as perfect as we thought? Today, we're going to peel back the layers on this so-called unbreakable tech and see if we can find a crack in its quantum armor.
So let's just cut right to the chase. Here's the big question. Is this technology, which is literally built on the fundamental laws of physics, actually foolproof? For the longest time, the answer from just about everyone was a very confident yes. But well, some brand new discoveries are making us all take a much closer look.
Okay, so before we get to the new stuff, let's talk about the myth itself. Why were we all so sure that quantum communication was the holy grail of security? I mean, where did this idea of it being completely unhackable come from? It all boils down to one single, really weird principle of the quantum world.
And that principle is called the observer effect. See, in the bizarre, almost magical realm of quantum mechanics, the simple act of looking at something, of measuring it, changes it forever. Think about it like this. Imagine you're trying to measure the temperature of a single tiny drop of water with a giant hot thermometer. The thermometer itself is going to change the water's temperature before you can even get a reading, right? That's kind of what happens here.
So this promise of perfect security really stands on two main pillars. First, you've got the observer effect we just talked about. A spy can't peek at the data without leaving obvious footprints. And second, there's something called the no-cloning theorem, which basically says you can't just copy and paste a quantum state to check it out later. Put those two together, and the promise was simple. Any attempt to eavesdrop would be instantly detected. It was supposed to be game over for any hacker, or at least that was the story.
And now, we get to the crack in that armor. A really groundbreaking recent experiment has just challenged a core assumption about how that disturbance, that footprint, actually works. It introduces this whole new idea of something called quantum continuity.
And this is where it gets really cool. Scientists finally managed to build a thought experiment that Albert Einstein himself dreamed up almost 100 years ago. He always wondered what would happen if you could somehow watch a particle go through a slit. Well, in this modern version, they did just that. And what they found was, wow. Observing the particle didn't always cause this big, sudden, catastrophic change. Sometimes it was a much more gradual, continuous transition.
This really shows you the shift in thinking. The old view was all or nothing. You look and bam, the whole quantum state instantly collapses. It's like a loud, blaring alarm bell goes off. But this new finding suggests that if you're really gentle, a weak observation might only cause a tiny, continuous change. A gradual degradation. It's not a shout, it's more like a whisper.
So the key takeaway here is that quantum behavior isn't always a binary on or off choice. It's not just a light switch. It's more like a dimmer switch with a whole continuous spectrum of possibilities in between. And that little bit of nuance, well, that changes everything.
Now I know, tiny deformation sounds pretty abstract and sciencey. So let's use a simple analogy to make this totally clear. Just picture a gigantic asteroid flying through deep space. So you've got this massive rock hurtling through the cosmos. Now imagine a single, tiny hydrogen atom bumps into it. Is the asteroid's path going to change in any way you could possibly measure? Of course not. The disturbance is so small it's basically zero. But here's the kicker. While you never notice the asteroid changing course, a super advanced observer watching that one little atom could actually learn something about the asteroid's speed and direction from the way the atom bounced off. The disturbance is real, it carries information, it's just way too small to be practically detected by the person who sent the asteroid. And that right there is the potential loophole. Okay, so we've got this theoretical crack, but how does a hacker actually use this? How do you turn this tiny, almost invisible disturbance into a full-blown security breach? The secret, it turns out, is in the engineering. Because at the end of the day, it doesn't matter if you're using quantum particles or old-school fiber optics. All digital information gets decoded into a simple 0 or a 1. And that decision is made based on a simple question. Is the signal that we receive strong enough to be a 1, or is it weak enough to be a 0? It's all about crossing a threshold.
So here's the hacker's playbook, step by step. First, Alice sends Bob a strong quantum signal that represents the number 1. Step 2, our eavesdropper, Eve, just barely interacts with it. She just siphons off, say, 1% of the signal's information. The disturbance is so tiny it just gets lost in the normal static of the system. Then, step 3, Bob's machine on the other end gets a signal that's 99% as strong. Sure, it's a little weaker, but it's still way above the line for being counted as a 1. So his computer says, yep, that's a 1. He has no idea anything is wrong. And now the final genius step. Eve takes her super weak 1% signal and just amplifies it. Because it was a 1 to begin with, her weak 1 becomes a strong 1. And just like that, she's recovered the entire message, and Alice and Bob are completely in the dark.
And all of this brings us to a really fascinating conclusion, one that actually takes us all the way back to one of the biggest scientific arguments of the last century. You kind of have to ask, in a strange way, was Einstein right all along?
You see, Einstein was never really comfortable with how weird and random quantum mechanics seemed to be. He famously felt that it couldn't be the whole story, that there had to be something missing from our description of reality.
So here's the real bottom line. There is a huge difference between perfect security in a physics textbook and practical security in a real-world system with all its noise and thresholds. The fact that this kind of weak eavesdropping might even be possible makes Einstein's old skepticism more relevant than ever. Now, to be clear, this doesn't make quantum communication useless, not at all. It just redefines its limits. It's incredibly secure, but maybe, just maybe, not magically absolute.
And that really leaves you with a final thought, doesn't it? It's this classic story of a beautiful, perfect theory running smack into the messy reality of engineering. And it makes you wonder, what's the next unbreakable truth that's about to get a major reality check?